Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. Scientists at the National Ignition Facility in California knew immediately that December 5, 2022 would assume its place in the annals of scientific history. By the time the U.S. Department of Energy confirmed that they had achieved fusion ignition, celebrations within the community were entering their second week. Around the world, captivated minds did their best to comprehend how a system of 192 lasers firing at a peppercorn-sized target could break down a barrier to clean energy that stood for close to 100 years. Today on All Things Photonics, we're joined by Jean-Michel Di Nicola, Chief Engineer for Laser Systems at the National Ignition Facility. Di Nicola's role in scientific history is one of indisputable importance to a foundational moment in science. The intricacies involved in getting an input of 2.05 megajoules to release 3.15 megajoules has represented a grand challenge for multiple generations of laser physics team leads. Di Nicola is the barrier breaker. As Di Nicola tells us, December's result has triggered more than ignition. It has led media outlets beyond the normal scope of science journalism coverage to a fascination with his work and its impact on the future of energy systems. It has led to an influx of job applications at the National Ignition Facility, as well as heightened awareness on fusion funding, startup companies, and fusion methods. Most of all, the fusion breakthrough has charted a new course for scientific possibility, with future progress dominating the forecast. News editor Jake Saltzman with the National Ignition Facility's Jean-Michel Di Nicola is up next.
So it's been now here about 11 weeks or 3 months since Lawrence Livermore National Labs announced the breakthrough results that will build our conversation around here. And that's a huge testament to the work that you and your team were able to put together and put in. But 3 months in the grand scheme of things, this was a pursuit that spanned decades, not all that long. But I do want to ask you about that very interesting time period. What's it been like since this result was reported in December?
Yeah, well, obviously, we received lots of publicity and congratulations from all over the world after this announcement. We also received a significant number of increase in our applicants for job openings, which is great news for us. Having more people being excited about the ignition and the inertial fusion energy is a treat. Our team members have also happily answered many interview requests, which is always interesting and gives a different perspective about the way that will work and how it's perceived. We have received renewed support from our sponsor. Our sustainment program is getting more traction and funding. We have an amazing laser facility. We'll go in more detail later on, but need to point out that it's a 20-plus-year-old for the conventional side of the facility, so we're due for some maintenance. Along the same line, I think overall we received more interest about our plans to push that envelope even further in terms of the National Ignition Facility, but also engaging with private sector. And last but not least, increasing the awareness of the public for energy and ignition has never been higher, which is great for all of us.
What's so fascinating about this, and I by no means consider myself an insider, but we've talked to, on the podcast members of the LaserNet US Consortium and people who work in or around big light sources. And it was no secret that your group and others were really on the cusp. It was within reach, this ability to return a net gain. And now you've done it. Is it interesting or surprising at all to see the likes of Vice and these outlets that really don't typically cover, even in some cases, science with such a high level of interest in your work?
Well, yes, you're right. The quest for fusion using laser has not been secretive pursuit at all. It has been a grand challenge since the invention of the laser, actually. And we have done that at Lawrence Livermore National Lab for two reasons. As a national lab with the U.S. Department of Energy and Nuclear Security Administration, where reaching ignition is very relevant for deterrence. But also since the early days, the lab has the idea that we want to pursue fusion for peaceful energy productions that could supplement existing production methods. So I believe that with the December 5th experiment, which, by the way, created about 3 megajoule of yield through fusion reaction with 2 megajoule of energy, laser energy deposited in the target. However, we have always been clear that we're not yet at what we would call net gain, because the electrical supply that we drew from the grid to power the laser is at about 300 to 400 megajoules. So the goal of NIF was never to put energy back on the grid and produce energy. It's a scientific breakthrough, scientific break-even, have a larger than one gain for the target. To get back to your question, I truly believe that the excitement comes from two things. First of all, releasing more energy than the laser energy we use to trigger the reaction is something like is magical, mysterious, awesome. It really triggers, excitement from the public, even if you don't know the science behind it. That's a big factor. And then second, I believe that we are living in a world in transition and transformation with a lot of anxiety being generated by climate, carbon emissions, different events around the world, creating some energy crisis, scarcity of resources, price increase, natural resources on gas and others. So in this context, I believe it's a natural reaction from the public to be enthusiastic whenever there are some good news, and they're probably too rare, in the news lines.
Di Nicola's use of the words magical, mysterious, and awesome should begin to take you back to the buzz that dominated mid-December 2022. Those are the words that will always characterize NIF's breakthrough, even years from now, when hopefully we have come to see fusion in a light far more commercially viable than we do in 2023. Like Di Nicola says, the goal of NIF was never to put energy back on the grid. The fact alone speaks to the progress still to come in the laser fusion space. He chooses the phrase scientific break-even to qualify December's result.
One of the things also that was, I think, very well done by the Department of Energy in sharing the December result was they brought in members of the team who work in different facets, intertwined obviously, but different facets. You're really on the laser side. Can you take us inside the room where these conversations take place? Just to be a fly on the wall would be fascinating, because the conversation obviously spans laser technology. It spans environmental considerations. What's it like to be part of that working group?
Well, to be part of this working group was really, amazing. It was like a surreal, out-of-the-body experience. If you are really specifically referring to the briefing that we gave on the December the 13th, it's typically the type of briefing you watch on TV. So being here, representing the entire team of thousands of people, literally, for the expert in the panel, were 6 of us, was truly amazing, an humbling moment. And we were all aware of this historic, announcements that we were delivering to the public. So that was really joyful, exciting, a little bit stressful as well, as you could imagine.
Absolutely. And this is just a podcast. This is an audio medium. I can only imagine when you add the cameras into the equation. And I'm glad you mentioned just now the fact that this team, when we talk about the notion of team, it's really big. There are a lot of contributors who are doing very involved and meaningful work. And the comparison I'll make is if you watch a World Cup match or any high level sporting event, at the end of the finals, the winning team, you see the athletic support staff, the trainers, everybody involved is celebrating. And I'm curious if that was the case here, because you have so many highly skilled workers in optics and components who, without their support and their efforts, this isn't possible. For some of those people who weren't in front of the cameras, what does this result mean?
Well, it was literally for some of them the accomplishment of all their professional life, no short of that. There were celebrations at multiple places, especially in what we call the control room, which is inspired from NASA. This is where, all the experiments are conducting and taking place. There was a huge celebration and with a broadcast live of the December 13 announcements. Where people could gather, congratulate themselves, and sort of truly enjoy this historical moment.
And this is obviously much easier to do on via a visual platform, but I'm going to ask you to do it anyway. Take us inside the NIF facility if you can, because it is a magical place and it's in the news now, certainly more than ever. You have a control room, you have these massive light sources, and a whole lot more. What's it like inside? If you could walk us through.
Sure. Actually, I think it's a very interesting exercise. That's probably the most interesting exercise, without the visuals, just trying to take you by the hand and drive you through this journey and through this entire, amazing facility in like 2 minutes or so. First, if you start from a bird's eye view, you're imagining flying over our facility in Livermore, California. This is the size of 3 football fields. It's quite amazing. The building footprint in metric is about 120 meters by about 220 meter or so. Just to give people that are not familiar with large buildings, this is along the longest dimension. It's comparable to one of the edge of the Great Pyramid of Giza. It's quite amazing. We're doing big science with the highest precision and accuracy that you can get in small experimental scale. From the side of the building, you're pushing glass door and entering the lobby where we have different types of exhibits and explaining how the laser works with different laser components. And quite amazing that after going through another series of doors, you can literally enter one of the laser bays. We have 2 laser bays. Those laser bays are literally like a cathedral, a temple, a pyramid of concrete, steel, and glass. Each laser bay is about 120 meters in length, ceiling of 3-story high, so it's quite amazing volume that you are entering. It contains laser glass, amplifiers, lenses, mirrors for 192 beam, and each beam is not your typical laser pointer beam. It's a beam that has a size of 40 by 40 centimeter in aperture. So that's for the laser. Now, using a series of elevators and stairs, you can enter, another area where the experiment is actually taking place. Going through heavy concrete shield doors that are closed during, thermonuclear experiments, you're entering what we call the target bay. It's a very vast 8-floor area where all the beam converge on a spherical chamber. The chamber by itself is about 10 meters in diameter, made of aluminum with concrete, around it. And that's where the reaction takes place after we insert a carefully crafted target at its center. We also have around the chamber incredible set of diagnostics that are used to understand the experiment in every aspect. Neutron yield measurements, spectrometers, imagers to understand how matter is and the target is compressed, X-ray emission, and implosion of the core. So it's quite an amazing scale. And even through videos, it's kind of hard to have a good rendition of what you feel when you are inside this building. So if you are in California, you can reach out to our public affairs and get a tour schedule. We'll be glad to have you in.
In fact, senior members of our editorial team did reach out and get a tour. And one of the ways in which they described this facility, in addition to magical and sort of, this majestic light source facility, was that it was a photon factory. This is a unique environment, not just now that you've achieved this tremendous result, but it's really, I don't know if specialized is the right word, but my question is, what's it been like for new members to join this team and adopt this mindset that ultimately gets you this type of a result?
Well, I joined back in the time frame of 2008, 2009, and really for me, the goal was to reach, to be joining this team, which has been known since the 60s to be really extremely rich and fertile ground for inertial confinement fusion. It's like the pinnacle. You are using the analogy with the World Cup. It's really like you are playing with the World Cup champions, so to speak. So that's the first, more sort of emotional aspect, I would say. Now, your point about photon factory, large scale, yes, this is big science. So there is definitely a paradigm shift. You are no longer by yourself in a lab in a small scale controlling your experiment. You need to adopt methodology, rigor, procedure that would allow you as a team to be successful. It's a paradigm shift from this point of view. Not to say that there is no creativity, no spontaneous discovery and results that are accomplished, but when it goes to performing this type of experiment, hundreds of people are involved in this experiment. It's comparable to LHC or other large-scale facility, and they can't be any improvisation on the fly about what you do. So it's definitely a learning process, and that's for the better. And the results speaks for themselves.
As a member of a 1,000-plus member NIF team, Di Nicola's charge is to oversee the operation of the all-important laser system. These refinements span the components and materials that enable the laser to perform, to added precision in the area of beam delivery. The nature of the ignition experiment itself will also influence the optimization of the laser.
The laser system that you're working with, or systems that you get to work with, in so many ways have more in common with the sun than the industrial fiber laser that we often write about here at Photonics Spectra. But nonetheless, right, you are a laser scientist at your core. My question is on the laser side. Is there anything that's happened in that technology area that allowed this result? I mean, has anything happened, just strictly speaking, in terms of laser technology that guided you in the last 5 or 10 years towards this current state of fusion?
Well, I wouldn't say that's one thing. That's the beauty and also the difficulty of that game, that you need not only from a laser point of view, a lot of different improvements, and those improvements have been sort of incremental. There is not one flipping of the switch breakthrough. We could go on and cite a few of them since the 70s, the 80s, the 90s, and more recently. I would say that, to get back to your point, more recently, to be allowed to safely and in a sustainable manner increase the energy of the laser throughput, and finally allowing ignition fusion, there has been a few things. First of all, the energy and power is important, but it is not enough. So we have been working very aggressively to have more precise delivery. Brute force is not enough. So from the fiber optics point of view, over the last 3 years, we completely refurbished our master oscillator room, which was 20-year-old, and we benefited from all the advances in fiber optics technology. That's where the two sort of meet. Also, from an optical point of view, optical components point of view, those components are exposed to tremendous amount of light and fluence, and it has been a continued improvement from material fabrication processes to harden them and make them more robust and be able to drive the energy higher, and also understand the different debris that are emitted from the target and how we could mitigate those debris to perform those experiments at higher energy in a sustainable way. So that's from the laser point of view, not to say that we're shaping the beams in every aspect we can. We're shaping the time aspects of the beam, because we need to have very precise delivery in terms of the pole shape, the power as a function of time. We're also shaping the beam through optically addressable light valve to flatten the beam in space as much as possible. We already said they are about 40 by 40 centimeter in size, but they need to be very flat because we don't want to have any hot spots that could potentially lower the lifetime of the optics. And we're shaping them also spectrally. So that's the laser side of the advances over the last, I would say, 5 or so years. And then there'll be many others I'm not expert of, but from a target fabrication point of view, target diagnostics, as well as the way to design the experiment so we achieve the maximum compression and finally trigger the ignition reactions.
This might be human nature, I don't know entirely, just to, whenever there is great news, to put it in perspective. In December, the news of a net gain was shared almost universally with this caveat that, yeah, we this is a great result, but there's still a great deal of work to come. before we're in a position for fusion to contribute to the energy problems that we face as a society, already face as a society. What is your take on that perspective? Because you can't disprove it, but you can probably position it in such a way to not distill or to not detract from the work that's been performed already.
Right. So first, I mean, during the official announcement on December the 13th, the entire team made it clear. As scientists, it is our duty to be clear with the public and not build false expectations, especially in a time that some are doubting science. We truly compare what we accomplish with a Bright, brothers moment as they took their first controlled flight in an airplane. Keep in mind, it took them about 11 years to complete the first commercial flight after this first demonstration was completed. So it's impossible to truly forecast when a power plant based on fusion magnetic or laser driven would be put on the grid. It would especially depend on the amount of private and public investment made to that effect. But to me, it's not unreasonable to imagine that we would see first prototypes in 10, 20 years from now if the ecosystem of funding between public and private align. So I'm a strong advocate, as you can imagine, for fusion. I wouldn't like us to get complacent and defer our net zero emission goals efforts with renewable, conventional nuclear power plants, et cetera, and just simply wait for fusion. At the same time, now the time is ripe, so we need to prepare for the next moves that are really enabling for humankind with fusion reactions and producing electricity through this outstanding, peaceful, and sustainable source of generating electricity.
Jean-Michel Di Nicola's 2023 Photonics West keynote explored recent laser performance improvements at NIF in the context of December's results. For reference, NIF contains a 192-beam, 4.2 megajoule neodymium glass laser that's frequency converted to 351 nanometer light, or 3 watts. The laser has undergone considerable tweaks, leading to considerable improvements over the course of its lifetime. Now, through laser-only experiments, the laser team at NIF is hard at work testing for improvements that aim to produce a power increase from the December 5th experiment in the area of 8%. All the while, the team is entering its final phase of fiber optics technology upgrades, aimed at system modernization.
Your keynote session at Photonics West was understandably quite popular and quite successful, I think, just in terms of topic and timeliness. Taking the full operation out of consideration for a moment, would you walk us through the next steps and the next goals for the laser system specifically as we move forward here?
Sure. We're very busy now, as you can imagine. We're conducting laser-only experiments, meaning that we're not using targets on a small number of NIF beamlines to test our recipe in terms of optics improvement, in terms of beam flattening and so forth, to be able to deliver 2.2 megajoule full NIF equivalent, which would be a 8% increase from the December 5th experiment, and also a 22% increase compared to the initial NIF requirements. And for that, we'll be, with that, we will be providing more margin to ignition. At the same time, we're also working, again, to the next step, enhancing the stability of the pole shape and the accuracy of the pole shape delivery by finishing up our last phase of modernization of fiber optics technology, electro-optic modulator, arbitrary waveform generator, to stabilize, get even a better delivery to the target.
The team, and I'll put you into that mix here, has already articulated plans to design experiments and in field shots with additional energy from the laser this summer. And the aim there would be to increase the margins for ignition and sort of chart a course for target gains. Just in the context of the overall pursuit, to move this onto the grid, can you speak to the significance of what the next phase of overall work means now that we've obtained this long-coveted result?
Right. Well, I think that, like any scientific approach, we'll be reproducing this experiment We did that following the August 2021 experiment, understand variability, sensitivity to initial conditions for the laser and the target. Compared to August 8, back in December, that was again 8% more energy. In the summer, we would be delivering yet another 8%. And we want to explore two axes. One axis is to achieve more robustness, and then higher target gains. We can do that through higher energy outputs, improved target fabrication, or even more optimized designs. Those two steps are important to better understand ignition fusion conditions and ultimately how we can get high yields with the laser energy as low as possible, especially with the focus for energy production and efficiency.
Steady and timely funding streams are obviously critical to the ability to move forward with any scientific pursuit. And I think with heightened interest and heightened focus, at least the possibility for added funding or new funding streams rises to the fore. What aspects of this quest towards inertial fusion energy require the greatest amount of funding? Because I know we've talked about the age of the infrastructure and some improvements that could be made there, but we really now have a full ecosystem.
Well, I think it's most needed, speaking for my own field, laser driver technology needs to be improved. What we are doing, a few times, a month would need for an efficient energy production to be performed multiple times a second. There were initial draft of inertial fusion energy power plants that would work with a repetition rate of 10 hertz, so 10 times a second. So to do that, NIF was never built to do that. It's a flash lamp pumped. We would need to go to much higher repetition rates. Diode pumping, if we stay in the solid state approach, is probably the way to go. So that will need engineering, cost reductions, laser physics, architecture, design, and also from a target fabrication, performance and cost. With 10 hertz, if you want to run for an entire day, you're approaching 1 million of targets that you would need to shoot per day. And again, from an economics point of view, you want to make sure that those targets are as cheap as possible to lower the price of the electricity production. Then last but not least, obviously the blanket material, neutron flux resistance, which is synergistic with magnetic fusion, will need sort of an influx of brains and funding as well to overcome numerous issues of brittle and damage resistance of those materials. Obviously, the physics will need to be explored further, as we described. We are now pushing the energy of the laser, but ultimately you would like to achieve very high yield with as low as possible energy from the laser. So it's going to take some extra steps and smarts. And then the entire plan would need to be designed and optimized for economic viability.
Have these blueprints been laid, or is this sort of just a fantastical desire? Are there plans for an upgrade, whether it stemmed from this latest result or otherwise?
There are plans and very real projects started from a national ignition facility point of view. But again, the goal of the national ignition facility never was and never will be to put energy on the grid. About energy productions, there are multiple articles and papers and very detailed concepts that have been put together using different sources, different drivers. And I think now we are at a time where, all those ideas that are on the table will need to be investigated further and see which one have the most value to be pursued from a, private and also government standpoint.
The startup environment in the fusion space. Now, this is not strictly laser fusion, but you do have Marvel fusion and X fusion and now Longview fusion. There are others. What type of eye do you keep on their pursuits and their activity? Because it is, as I mentioned, this ecosystem, it is becoming sort of a family now.
Yeah, so absolutely. And we definitely have assets and we can bring things at the table. And we started engaging with some of the names you mentioned at a low level, but we expect that this engagement would rapidly increase with more collaborations and partnerships agreements fully in place. I truly believe it is synergistic because private sector can sort of bring things at the table that national labs can't, and vice versa. So making that an ecosystem on some of the models that you mentioned is really critical to make it happen.
If I had to guess, the December 6th result has created a few more, we'll say, fusion fans than there were before. Certainly people who are thinking and considering fusion. And I think that our audience here on the podcast, just given the nature of what we do, doesn't really need much convincing on the potential or the science behind laser fusion. But nothing is ever totally universal. So I'm curious if you've had to develop a pitch to those who, one, may lack the knowledge to comprehend the significance of this result, or maybe more pertinently, who just don't believe that this experimental result carries much weight until we see something more commercial.
Right. Again, I mean, the December 5th was an incredible scientific breakthrough. It is up to us as a nation and also as citizen of the world to do the right thing about it. We're living times of changes with climate, carbon dioxide emission, different events around the world, creating some energy crisis. We can act now using well-established and known methods to combat those effects, but at the same time, prepare a future that is bright. Either magnetic or laser fusion have incredible potential to power our societies in the future in a peaceful and sustainable manner, in a virtually limitless way without scarcity issues. So if that's not a pitch, if people are not convinced, I honestly don't know what to do.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.